Engineering a concrete dam requires balancing the immense static weight of the structure with the pressurized movement of water bypassing it through the foundation. Whenever there is a difference in water elevation, what engineers call hydraulic head, water is forced through the microscopic pores of the underlying soil. This flow is called seepage. To prevent catastrophic washouts, engineers have to precisely quantify this seepage volume. Calculating this entirely through abstract differential calculus is difficult, especially when the site boundaries are complicated. We need a way to physically map the geometry of this groundwater flow, because if we miscalculate it, even the strongest surface structure will inevitably collapse. The solution is a geometric tool known as a flow net, representing steady-state fluid flow. First, we draw flow lines, mapping the physical paths water molecules take to reach equilibrium. Second are the equipotential lines. These are contours representing points of equal energy. As water moves along a flow line, its energy drops consistently at each of these contours. In uniform soil, a strict rule governs this system. These sets of lines must always intersect at exact right angles. This strict orthogonal matrix transforms complex equations into visual geometry. To see how this calculates flow, we look at its fundamental building block, the elementary square. This isolated shape has two variables, a specific vertical length and horizontal width. Because of the strict right-angle rule, we draw the net so these dimensions are perfectly equal. Applying Darcy's law, flow equals permeability times hydraulic gradient times cross-sectional area. Gradient is head drop divided by length. Area is width times unit depth. Because length and width are equal, they cancel. Flow through any square is permeability times head drop. Water is incompressible. That means the exact volume entering one square must exit it and pass right into the next. Therefore, the calculation derived for a single isolated square actually represents the continuous flow for that entire flow channel. To scale this up and calculate the total seepage under the structure, we step back and count the macroscopic grid elements. In this model, we have 4 distinct flow channels and 14 total potential drops. Dividing total hydraulic head by potential drops gives the exact head drop across any square. Multiplying that by the number of flow channels gives the final discharge. We've derived the total volume of water threatening our excavation using basic geometry. The flow net serves as a visual map of how energy dissipates within the soil mass. As hydraulic head forces water through the microscopic pores, that water loses energy to viscous friction against the soil particles themselves. This friction physically transfers a continuous drag force directly onto the soil skeleton. We call this the seepage force. The magnitude of this threat per unit volume is equal to the hydraulic gradient multiplied by the unit weight of water. This becomes a critical problem when the direction of flow is upward. In that scenario, this frictional drag actively fights gravity. If this upward drag exactly equals the submerged weight of the soil, the effective stress drops all the way to zero. This zero stress state is the mechanical definition of a boiling condition, often called quicksand. It is a fatal geotechnical flaw that turns solid, load-bearing ground into a liquid trap. Beyond volumetric flow and macroscopic failure, the flow net hides one more crucial set of data: localized pore pressures. When analyzing an earth dam or a slope, engineers need to know the exact internal water pressure at specific subterranean points to determine if a landslide is imminent. This technical diagram shows an earth slope's flow net. To extract internal pressure, we locate our target depth, point Z. We trace its intersecting equipotential line upwards. The vertical distance from this top intersection down to our target establishes the piezometric head. By translating fluid dynamics into an orthogonal geometry, the flow net empowers engineers to instantly visualize and extract the invisible forces holding our infrastructure together.